The third lecture on AC circuits. In the earlier class, we have seen that when there is a reference current I, if we denote it by the current phasor, then the voltage across resistor is in phase with the current. The voltage across inductor leads over the current by 90 degree, and the voltage across the capacitor lags behind the current by 90 degree. And this theory is applicable for series circuits, series combination. And when we have a reference voltage V, the phasor is this. The current phasor across the resistor is in phase with V. The current phasor across L lags behind V by 90 degree, and the current phasor across capacitor leads over V by 90 degree. And this theory is applicable for parallel combination. We shall apply this theory. This is the summary of what we have done in the last two classes, and today we shall apply this to simple AC circuits. In this class, we shall consider the LR circuits. That is a circuit comprising of an inductor and capacitor. First, we consider series LR circuit. Series LR circuit. So the thing is that we have an inductor of inductance L, a resistor of resistance R. They are connected in series, and the combination is fed by an AC voltage V as a function of T is, and this is at a particular instant. This is the current phasor. So the voltage phasor across this is VL, and that across R is VR. We shall analyze the circuit in two different ways. But firstly, we shall solve this equation by solve the problem by solving the differential equation. The Kirchhoff's voltage law applied to this AC circuit becomes VR plus VL is equal to the applied voltage V. Now, if we write it in terms of its magnitude, this becomes R into I, and this becomes L di dt is equal to V is equal to V0 e to the power j omega t. Since it is a series circuit, so same current I flows through both the elements, so we have written I. Now this equation is an inhomogeneous first order differential equation. So it's complementary function. Complementary function is L di dt plus Ri is equal to 0, or this equation can be written as di I is equal to minus R by L dt. We write it minus dt by lambda, where lambda is equal to L upon R, and it has the dimension of time. You can check that lambda has a dimension of time, or it is better to write it tau. Let me write it tau. Tau called the time constant, whose significance will be apparent very soon. The solution is I as a function of t is equal to some constant a e to the power minus t by tau. This shows that the current corresponding to the solution of the homogeneous equation, which is the characteristics of the LR circuits, irrespective of the source, this dies down exponentially, and the time taken to die out this current depends on tau, and that is why tau is called the time constant. When t is equal to tau, the current falls to 1 by e times of its initial value. So the greater the tau, greater will be the time taken to die the current. And a particular integral, but pi, note that initially if we suppress this term, the solution is this solution dies down, and ultimately the current in the circuit changes in tune with the applied voltage. So we write the particular integral, we use the trial solution as I at t is equal to I0 e to the power j omega t. The I0 may not be any real quantity. So if we want to find out I0, we use this trial solution in this equation. So we get R I0 e to the power j omega t. E to the power j omega t will be common to everybody, and for this, if we differentiate this is j omega L I0 is equal to V0, or we write I0 is equal to V0 by R plus j omega L. We introduce the reactance of the circuit elements. In terms of reactance, it is XL, where XL is equal to omega L. We see that for resistive circuit, we know that I is equal to VR, where R is real. Here we see that the resistance offered by a combination of inductance and resistance is a complex quantity, and it is called the impedance. One define, which is a complex quantity Z. For this series LR circuit, it is R plus JXL, which is R plus J omega L, and we can write it as the magnitude of Z is R square plus omega square L square, and the phase angle is given by tan inverse XL upon R is equal to tan inverse omega L upon R. So this is the phase factor. Now coming back to the phase is 0 as omega is equal to 0, and as omega tends to infinity, this phase tends to plus pi by 2. So the phi variation of phi is, this is so the phase variation is of this sort. This is the variation of phase. Now if we come back to this equation, this can be written as V0 upon Z This can be written as V0 upon mod Z e to the power j phi. This is V0 mod Z e to the power minus j phi. This is for I0. So we write I as a function of time is equal to I0 e to the power j omega t. This is equal to V0 by mod Z. This is a real quantity e to the power j omega t minus phi. So we see, comparing this expression with the voltage, that current through this series LR circuit lags behind the voltage, applied voltage by a phase angle phi, which is given by this. The phase is 0 at 0 frequency and tends to pi by 2 at high frequency. Let me keep this term for comparison. We shall solve this equation then by Phasor diagram method and see where we land upon. Okay. Before going to the Phasor diagram method, let me draw the graphs variation of this. So we have, this is the time axis, this now the applied voltage. If we consider that the voltage is given by the imaginary part of this, then it is the sine curve. This is the sine curve, and the current lags behind this. So current will appear or reaches its value. This is current, this is voltage, this is voltage. And if we consider this one, this part, that is the equation solution of the CF, the CF dies down like this. So ultimately we will get the very sinusoidal variation of the current when the circuit is fed by a sinusoidal AC source. Now let me try to solve this equation by using the Phasor diagram method. At a particular instant, let the voltage applied be represented by a line segment. Let us consider at a particular instant, this is the current phasor, and the corresponding voltage phasor is this, VR phasor. This is R times I, and the VL phasor is this, VL is equal to XLI, and here we have JXLI. So if we add these two vectorically, we get the applied voltage phasor this, and note that this is also the I phasor. So we write in vector notation VR plus VL is equal to V. So if we write the magnitude of V, first thing, this is equal to R into I, and this is equal to j xl I, and this we write is equal to zi. So if we write the magnitude equation, z square or z modulus square is equal to r square plus xl square, that is equal to r square plus omega square l square. This is the magnitude, and this vector makes an angle with this is phi. So tan of phi is equal to this much by this much. So we get the same solution, and we find that from this equation we get that V is equal to zi. So we can write I is equal to V by Z in terms of, this is in terms of phasor. So if we come to the instantaneous value, this becomes I0 j omega t is equal to V0 to the power j omega t plus z is equal to r plus, and this leads to the same equation that we have obtained over here. Now let me come to this. This is the V applied voltage, and this is VR, and I is in the same direction. So you see that this phase angle has been traced in anti-clockwise direction, so phi is positive. So V is advanced in phase in compared to I. Since we have fed the circuit with an AC voltage source, AC source, so we with reference to the applied voltage, the current lags behind the applied voltage. So I lags behind the applied voltage. We have solved the things by two different ways, one by solving the differential equation and one by solving this equation. Now we define the voltage gains. This is a very important concept. Voltage gains and filtering action. If we measure the RMS value of voltage, if we use any meter to measure the AC voltage, we generally measure the RMS voltages. So if we measure the voltage across the two ends of the resistor, we get the RMS value of the voltage, and if we measure this, it will give you the input voltage. So voltage gain across the resistor is given by, this is V for voltage gain, this is across R, it is a function of frequency. This is defined as, we know that this is R into I by Z into I. So this is R by mod Z. So this is R by R square plus omega square L square under root. Now let me define the voltage gain across the inductor or inductance. This is similarly defined as VL by V, and this is XLI by ZI, and obviously there is J. So this is equal to omega L upon r square plus omega square L square. When r omega is 0, this is 1, because this is 0, this is 1, and when omega tends to very high value, this becomes 0. So it has two limits. One is omega tends to 0, it tends to 1, and omega tends to infinity, it tends to 0. Similarly, if we consider this one, when omega tends to 0, it tends to 0, and when omega tends to infinity, this tends to 1. So if we draw a graph of voltage gains, this is the frequency and this is the voltage gain, and this is the 1 line, this is 1, this is 0 line. So this starts B. If we compare the voltage gain, we see that the low frequency signal, if we want the low frequency signal to be received, then one must calculate the voltage or measure the voltage across the resistor, and because for resistor the voltage gain across the resistor is appreciable at low frequencies and it dies down or decreases rapidly at high frequencies. On the other hand, the voltage gain across the inductor is low at low frequencies and becomes appreciable at high frequencies. So it acts as a high pass filter, that is high frequency signal are passed easily, high pass filter, and this acts as low pass filter. And high and low pass filter, they are equal, these two voltage gains are equal at this called the cutoff frequency. The cutoff frequency is 1 at which these two are equal. So at cutoff frequency at omega is equal to omega c, since the denominator are the same, we must have r is equal to omega CL, or omega c is equal to r by L. Note that this is equal to 1 by tau, the time constant. So this is a particular feature of the series LR circuits. Now, although in practical life the parallel LR circuits are less frequently used in comparison with the series LR circuit, still due to the academic interest, we shall investigate the parallel LR circuits and we shall carry out the corresponding calculations. So the the circuit is something like that. We have an inductor and we have an resistor. They are connected in parallel and the combination is fed by an AC voltage source. Now, at a particular instant, the current phasor is I, and this current if we consider the voltage phasor is at a particular instant, it is the voltage phasor and the current phasor. The voltage across both R and L are the same because they are the parallel circuits, but the current gets divided over here. This is the current phasor across R, and this is the current phasor across L. So if we apply KCL in its AC mode, it is IR plus IL is equal to the applied total current. Now we know that I is if we write it like this, we know that this is V by R IR, and for this we know that VL is equal to LD IL dt. So if we invert it, IL is given by 1 by L integration VL dt. So this is okay. If we write it in differential equation form, this is V by R plus 1 by L V dt is equal to I. This is I0 to the power j omega t. So for this case we write I, the current to be sinusoidal, and we have written it like this. This part may be confusing, so it is being supplied by this. We differentiate this, so we write it as the CF of this equation is complementary function. Complementary function of this equation is dV by V. This is a complementary function is obtained by solving the differential equation R dV dt plus V by L is equal to 0 when there is no source term. So this leads to dV by V is equal to minus LR dt is equal to minus dt by tau, which gives V as a function of t is equal to some constant A e to the power minus t by tau. So the solution of the complementary function dies down with time, and for the PI we write PI, we are asking for a solution of V, so we write V0 e to the power j omega t. So if we plug this into this equation, this is j omega V0 by R, and this is V0 by L. This equation together with this solution gives, and on the right hand side we have I0. We want an expression for I, so we write I0 is equal to V0 is common, and we divide both the sides by j omega, so it is 1 by R plus 1 by j omega L V0. You note that in AC circuit we define V is equal to Zi, where Z is called the impedance. Here we write I is equal to Y by V0, where Y is called the admittance. This is impedance. And this is called admittance. So we write complex admittance as, let me use this part of the board. Complex admittance is defined as Y is equal to 1 upon R plus 1 upon J omega L. This is 1 by R plus 1 by J XL. We write it as, because this will be minus, we write it as minus J theta. Note that for the series combination, or in case of Z, we use the phasor as phi, and here we have used the phasor as theta, and where the modulus of Y is governed by 1 by R square plus 1 by omega square L square root, and tan of theta is governed by 1 by XL by 1 by R is equal to R by XL. So writing in this becomes R by omega L. As omega is 0, this is infinite, so theta, omega and theta relation, theta is equal to 0, omega is pi by 2, and when this is very high, it is 0. So the variation of theta, the phase angle for parallel circuit, is reciprocal to that of the phase angle for complementary to the phase angle for series circuit. We may draw the phase. Now let me come to the value of current. So this is written as mod Y e to the power minus J theta V0. Now if we write it in terms of instantaneous quantities, we find that V0 is equal to I0 by mod Y e to the power J theta, or V at instantaneous value, V at t is equal to so the V, the current voltage leads over the applied current by a phase theta. Let me check it by phasor diagram method. Here, since the circuit is a parallel combination, this is the voltage phasor at a particular instant. So this is the corresponding current phasor across the resistor, and this is the current phasor across the inductor. So if we like to add these two, I will get, this is IR, this is IL. If we add this, it will be the I and P is in phase. So you see that P is ahead of I in phase. This is the expression, and this angle is theta. And similarly, we can define the current gain and the current gain across the resistor and the inductor. The current gains in the case of series circuit, we define voltage gain. Here we define the current gain GIR, which is a function of omega, IR by I, the same definition. And for I we write and the modulus sign, and this becomes VV cancels out 1 by R modulus of omega, so this is 1 by R, and for this part we write, if we simplify this, in the top we will have R omega L, so of which R cancels with this, so this is omega L by R square plus omega square L square. And similarly, if we draw the current gain across the inductor, this basic definition is IL the basic definition is IL by I. This on simplification becomes you can check it yourself. And if we measure current, which is not very easy in practice, but however if you can measure current, you see that the current gain is 0 for this at omega is equal to 0. So the low frequency signal, so for current is concerned, is blocked by the resistor, while the high frequency signals are being transmitted by the resistor. If we can measure current, in the books the current gains are not a very important concept so far as AC circuit is concerned, because it is not very easy to measure current, AC current directly. However, this is the theory, and to conclude the discussion, we shall consider an imperfect inductor. A pure inductor is one which has no resistance or capacitance. But in practical life, a real inductor may be looked upon as a combination of a resistance, real inductor. This can be looked upon as an inductor of inductance L together with a small resistance RL in series with it. So this combination behaves as a real inductor. A pure inductor is one in which there is no energy loss. The energy that it gains in a quarter is being pushed back to the source in the next quarter. And we have seen it in the first two discussion. But for a real inductor, since there is RL present there, some energy will be lost across RL, and that leads to a loss effect. Now the problem is to how to identify, have a measure of RL. I am going to discuss this one. We have this is L, this is RL, and this combination is the inductor. And the circuit is completed by a external resistor R, and the combination, this series combination, is fed by an AC voltage V. We take a RMS meter, and if we connect the meter between these 2 points, it will give you the input voltage V. If we connect it one over there and another over there, and this voltage is the voltage VL across this inductor, and if we connect another the meter between this, it will give you the VR, the RMS voltage across the resistor, and this gives the RMS voltage across of the input source. For a perfect inductor, we know that the Phasor diagram is like this. For perfect inductor, the Phasor diagram is this. This is VR, this is VL, and this is B. This is the for perfect inductor. But here we do say the RMS voltage is across resistance is 1 volt. This is 1.9 volt, and this is 1.6 volt. So what we do? So this is 1.0, 1.5, and say this is 1.9. So we take arcs of length, say 10 centimeter, 15 centimeter, and 19 centimeter. And firstly we take a, this is 10 centimeter, this is 10 centimeter long, which represents VR. Then with an arc length of 19 centimeter, we draw a line, 19 centimeter arc length, and from this point we take an arc length of 15 centimeters, say this cuts this. So what we do, we connect this and we connect this. In the actual case, this VL should be like this. No, I have made a wrong. If we do apply, if we apply the triangle of, then this is VR, then this is V, let me check once. Now this is the magnitude of VR. We take this, and corresponding to VL, say 19 centimeter, we take an arc length of 19 centimeter, and from there we take an arc length of 15 centimeter. The drawing may be appears to be different. This is due to the my difficulty in drawing. However, for the case of an perfect inductor, this VL would be perpendicular to VR. But due to the imperfection this it has been shifted by an angle delta L. So this is the direction perpendicular to VR, and this much is the deviation of VL from its ideal situation. This delta is called the loss angle. Delta L is equal to tan inverse RL. This is known as the loss angle. This loss angle is a measure of the energy that is being dissipated across the small resistance of the inductor. In the next class, we shall consider the ACCR circuits.